Chapter 5.4, Exponential Functions, Differentiation and Integration. Day 2, differentiate e to the x. All right, now, so y equals e to the x is the function we're going to look at right now. Right? So far, our rules for derivatives, we got the power rule, the product rule, the quotient rule, the chain rule, and implicit. None of those deals with what to do when we have a variable in the exponent. We do have a technique to kind of help us deal with that, though, where we take the natural log of both sides. So the natural log of y equals the natural log of e to the x. The x comes out front, the natural log of e cancels. We got the natural log of y equals x, which should not be surprising because they're inverses, natural log and e to the x. We'll use log differentiation. The derivative of the natural log of y is y prime over y. The derivative of what's inside over what's inside. And the derivative of x with respect to x is 1. Solve for y prime. By multiplying by y, we see y prime equals y, or y prime equals e to the x. So the derivative of e to the x is e to the x. All right? All that work to show that the derivative of e to the x is exactly the same. This is the one function that's its own derivative. That's theorem 5.11. The derivative of e to the x with respect to x is e to the x. If you have something in there besides x, applying the chain rule, the derivative of e to the u with respect to x is e to the u times the derivative of u with respect to x. All right, so let's use this. Let's do a couple problems. Let's find the derivative of e to the 2x. All right, since it's e to something, it's going to be e to whatever it is, because e to the x is e to the x. There's something up there. There's a function in the function, so we've got to apply the chain rule. Derivative of 2x minus 1 is 2. So the derivative of e to the 2x minus 1 is 2e to the 2x minus 1. For part B, we're going to rewrite that. I don't like to have fractions, so I'm going to rewrite that as negative 3x to the negative 1. That derivative is, well, e to the negative 3x minus 1. Just take the function you see there, and then take the derivative of the function inside. So that will be 3x to the negative 2. And if we want to clean that up, we got 3e to the negative 3x to the negative 1 over x squared. So the derivative of e times the derivative of whatever's inside. All right, find the relative extrema. All right, this is what gets tricky about this one, is because we got to go back and apply everything else to one derivative. To find extrema, we need to find the derivative and apply the first derivative test. So f prime of x, that's a product rule because we got two functions there. First derivative of the second plus second derivative of the first. Derivative of x is 1. Set that equal to 0 and factor. E to the x comes out. We got e to the x times x plus 1. Now, using the zero product property, e to the x will never be 0 because that's not in the range. But x plus 1 can be 0 when x equals negative 1. So our critical number is x equals negative 1. We will go through, do a sign chart, and check the left and the right. If I check 0, e to the 0 is 1. 0 plus 1 is 1. They're both positive. 1 times 1 is positive. So we can see our function is increasing after negative 1. If I throw in a negative value, e to the negative 1 is positive. Or I'm sorry, e to the negative 2 is positive. Negative 2 plus 1 is negative. Negative times positive is negative. So our relative min happens at x equals negative 1. And our relative min is f of negative 1, which is negative 1, e to the negative 1 or negative 1 over e. That's the lowest that function will go. All right, moving on. This is a calculator-based problem. Not an overly difficult one, but it's good practice. The number of shares traded in millions on the New York Stock Exchange can be modeled by the equation y that's given there, where t represents the year. T equals 0 is 1990. At what rate was the number of shares traded changing in 2000? Rate of change is our derivative, so we want to find the derivative at 2000. So t equals 10. All right? So this is a good review. We're going to want to find the derivative of y when t equals 10. Our derivative function for the calculator is under the math menu. It is the 8th choice. Okay? We're going to do the derivative with respect to t. I can change the variable in my calculator, or I can keep it the same. T is above the 4. I'd like to change it. We're going to do it with respect to x. So instead of having 3981 e to the 0.1715x, or t, I'll go 39,811, excuse me, e to the 0.1715x. And now when x equals 10. And so it is changing at a rate of 37,938, or 37,938 shares per year. All right. So we're just taking the derivative and plugging in 10. You can do that by hand too, but this is good calculator practice. Okay, find the derivative of these last couple problems. Find the derivative of 3e to the 1 minus x squared. Okay, we got a constant multiple there, so we're just going to multiply by the 3, whatever we get. So it'll be 3 e to the u is e to the u, 1 minus x squared, and then we need to take the derivative of u, which is negative 2x. Clean that up a little bit, we get negative 6x e to the 1 minus x squared. Take the derivative here. Now this is a natural log. So we want to make it a little easier by applying some of the log properties. I'm going to do a log expansion here. Y equals the natural log of 1 plus e to the x minus the natural log of 1 minus e to the x. All right, now I apply the log derivatives, which means the derivative of what's inside over what's inside. So dy dx, the derivative of what's inside the first one is 1 plus e to the x. The derivative of that is e to the x over 1 plus e to the x minus the derivative of what's inside the next one is negative e to the x over 1 minus e to the x. You can keep that or you can simplify it. It's not a huge simplification. E to the x plus e to the x over 1 plus e to the x plus e to the x over 1 minus e to the x. All right, our next one is just a review. What's the derivative of e to the x? That's a tough one. The derivative of e to the x with respect to x is e to the x. Okay, the derivative of e to the u with respect to x is e to the u times whatever the derivative of u is with respect to x. So it's e to the x. The derivative of e to the x is e to the x. If there's something inside in place of x, you still take e to the u, just multiply your result times the derivative of that u.